Hello and welcome. Today we're going to learn about digital to analog converters, and specifically we're going to talk about the various specifications that you might encounter when selecting a DAC for a particular application and what they all mean. Now first, let's talk about what a DAC actually is. You know, with all the talk about living in the digital age, the hard truth is that it's still an analog world of temperature, pressure, length, and so many other physical quantities, all of which can assume any of a continuous range of values at any time. It's also a hard truth that making sense of these values is usually best done in the context of a microcontroller running some algorithm in software. And that means converting the real-world analog values to a set of numbers that the algorithm can process. Now, once the microcontroller's finished with the signal processing jobs, you have to get the results back to the real world again, and that's the job of the digital to analog converter. Now, in the real world, signals can change at any time, and they can adopt any value within certain broadly defined ranges. But in the digital realm, signals are really just a list of numbers, values sampled from the real world at regular, precise intervals, or values synthesized by an algorithm that models a real-world process. A DAC, then, converts this list of numbers to a time-varying signal, usually a voltage, ready to be used in the real world. Let's think about those numbers for just a moment. You might think that it would consist of the actual voltage values, but most frequently each value is just an integer that represents a value between some minimum and some maximum. For example, if your list of numbers consists of 8-bit values, then each number on the list can assume any one of 256 values from 0 to 255. If the value 0 represents 0 volts, and the full scale range is exactly 1 volt, then the value 128 should correspond to exactly 1/2 volt. Well, that brings us to the first term that we need to define, the resolution of the DAC. Resolution defines the number of discrete levels the device can generate, and it's usually expressed in bits. An 8-bit DAC will have 256 discrete levels. A 10-bit DAC will have 1024 discrete levels, and so on. It's not uncommon these days to see DACs with 24 bits of resolution that can resolve over 16 million discrete levels. So it's easy to see how the system works. A microcontroller or a digital signal processor sends the values from the list one at a time to the DAC. And the DAC produces an analog signal that changes with each new number. But how rapidly can I send numbers to the DAC? Well, every DAC requires a certain amount of time to convert a digital sample to its corresponding analog level. And that time limits the rate at which it can process samples. That rate is called the maximum sample rate, and it varies from one DAC to another. Now, you might think that the best DAC for any application is the fastest DAC with the most resolution, but the reality is a little more complicated than that. Consider some typical use cases for a digital to analog converter. First, let's think about the case in which the DAC is used to generate a DC bias voltage. Maybe you need to bias an AC signal into the sweet spot of a detector, or maybe null out an interfering DC signal. In such a case, resolution and stability are going to be the most important factors. Speed? Not so much. The bias voltage likely changes really slowly. But what if the DAC is directly generating a modulated radio frequency signal? Well, now, it's all about speed, and, I'll filter any noise artifacts out in the analog world. Finally, consider the case in which the DAC is driving a mechanical actuator. Depending on the actual mechanics, you're going to need a mix of speed, accuracy, resolution, and stability. Look, the bottom line is this. No one DAC is perfect for every application. And in general, when we consider DAC specifications, it's convenient to group them into two categories: specifications that relate to static performance and specifications that relate to dynamic performance. Static characteristics relate to the fundamental properties of the device, like the number of bits of resolution, or those properties that are observable when the device outputs a static signal such as offset or gain error. Dynamic characteristics, on the other hand, are only observable when the DAC is changing from one code to another, or when a sequence of codes is producing a waveform at the output. Factors like settling time and distortion are considered dynamic characteristics. But, before we begin looking at the specifications in depth, we need to talk about the difference between accuracy and precision. Hey, it's not unusual to hear those terms used interchangeably, but they really do represent very different concepts. And you know what? As luck would have it, we have 3 expert archers who have joined us here to help illustrate the point. Okay, Archer 1, please step forward. Nice grouping, Archer 1. Just one problem. None of your shots actually hit the bullseye. Nice repeatability. The pattern shows a lot of precision. But those shots just weren't very accurate. I'm sorry, Archer 1. Nice try, though. Archer 2, please step forward. Well, Archer 2, you did hit the bullseye. Once. Your precision needs a little work, but your accuracy, that is your tendency toward the center of the target, is right on the money. Maybe you can do better with a little practice, Archer 2. Okay, Archer 3, show us what you got. Now this is what we want. The grouping is precise. All of the shots fall close to one another, and this archer is accurate. Every shot went right through the bullseye. Nice job, Archer 3. Now, look, the lesson here is that DACs can be a lot like our archers. You can get a DAC that's precise, but not very accurate, in that it might have a persistent bias away from the desired output voltage. You can get a DAC that's accurate but not very precise in that it's consistently near the desired output, but noise and other factors push it away from the target output voltage. Or you can get a DAC that is both accurate and precise that hits the bullseye every time. All right, then. With these preliminaries out of the way, it's time to start looking at the specifications for static characteristics. Now, we've already covered resolution. Now, remember, that's the number of steps between the lowest output value and the highest output value. And because most DACs have a binary input, the number of steps is usually an even power of 2. For example, an 8-bit DAC would accept 8 data bits on its input and would produce one of 256 discrete levels on its output. 256 is the number of states that can be represented in 8 bits. Now, if we have a voltage DAC with a full-scale output of 10 volts, then the smallest level change the DAC will be able to resolve will be about 39 millivolts. That is 10 volts divided by 256. And that should be true for every change of exactly one code. The difference between the output voltage, let's say, for the code 100 to the output voltage for the code 101 should be right about 39 millivolts. But here's the thing. Depending on the architecture of the DAC, making sure the difference between adjacent codes is exactly the same can be surprisingly difficult. And that's where some of the other static characteristics come in. Now, a good way to picture this is to create a plot with the digital input codes on the x-axis and the DAC output voltage on the y-axis. Ideally, you'd expect to see a straight line, except, of course, for the fact that if you zoom in enough, you'll see that the line is actually kind of a stair-step. That line should start at the minimum value, frequently 0 volts out for 0 digital input, and should end precisely at the maximum full-scale value. If the line doesn't start exactly at the origin, the difference is called the offset error. At the other end, if the line doesn't end exactly at the full-scale value, that's called the full-scale error. Now, If the offset error and the full scale error are exactly the same and in the same direction, then at least we can say that the slope of the line is correct. That is, on average, each step at least has the correct change from the previous step. But if the line has the wrong slope, then there is an error in the gain of the system, and you're going to have to account for that in either software or hardware. Now, the good news is that offset and gain are easy to compensate with a bias network or an amplifier. If the DAC is doing its job, you're going to get a good straight line from the lowest code to the highest, even if you do have to adjust the offset or the gain a little bit. Now, the problem is, real-world analog circuits aren't ideal at all. It's really not unusual for this graph to bow up or down or to have some other more complex nonlinearity. The amount of this deviation of the output from the ideal straight line, measured at its maximum deviation, is called the integral nonlinearity, or INL. And that's usually given as the number of least significant bits that the output deviates from a straight line at the maximum error point. Here's the main idea. Remember the difference between accuracy and precision? Well, INL is one measure of the accuracy of the converter, but what factors affect the precision? Well, we talked about one factor that dictates precision. That's the resolution. But other elements can affect precision too. What if the individual steps average to a straight line, but each step varies slightly from its neighbors? Well, that kind of imprecision is called differential nonlinearity. Part of the reason differential nonlinearity can be an issue is just the binary nature of the input. See, the voltage contribution for each bit has to be twice as precise in percentage terms as the next lowest bit. In our 8-bit example, the LSB switched 39 millivolts on and off. But the MSB switched half the full-scale voltage, or 5 volts, on and off, and that 5-volt output had better be precise to a fraction of the LSB output, which means the output has to be significantly better than 1% precise, and that's just for a cheesy 8-bit converter. And think about this. What if the more significant bits aren't all that precise? I mean, the consequence isn't just that the DAC isn't as precise as it might be. The problem is that you might find yourself in the situation in which going from, say, the hex 7F state to the hex 80 state actually makes the output fall instead of rising as you'd expect. But think about it. You're turning off 7 voltage sources and you're turning on 1. And that 1 had better be exactly 1 count more than the sum of the other 7. Are you beginning to appreciate how tough it can be to design a good data converter? All right, at this point, we really need to pause for just a moment and talk about units. So far, we've been talking a lot about measuring these parameters in terms of least significant bits. And hey, that's a completely valid way to discuss these matters, but the thing is, it's not always the most convenient or the most familiar way. And depending on the application, you might find yourself speaking a foreign language to an engineer when you start talking about LSBs. For example, it might be more convenient to talk about nonlinearity as a percent of full scale. Well, this especially makes sense in DACs that let you provide the full scale voltage as an external source. You might specify the maximum INL as 0.1% of full scale, and the engineer would know that if they set 10 volts as the full scale value, then the output for any given code might be as much as 10 millivolts off. Parts per million works like percent full scale, but it avoids the decimal point in most cases. The DAC we just described with an INL of 0.1% of full scale could also be described as having an INL of 1000 ppm. Decibels are a frequently used measure that operate on a logarithmic scale. You'll see dB used to express noise and distortion most frequently, but it can be used to express any ratio, just like percent or parts per million. Finally, it's not that unusual to see some values expressed directly in electrical units, most often volts, millivolts, or microvolts. Now, you might wonder, and not unfairly, with all these potential sources of error, does it even make sense to specify a particular resolution for a given DAC? I mean, wouldn't it make more sense just to declare how close to the bullseye you can expect to be when you present a particular code? Well, in some sense, the answer to that is a qualified yes. We can discuss a factor called the true accuracy of a DAC. And that's the accuracy adjusted for all these sources of error. For example, you might advertise a 12-bit DAC, but if it has an integral nonlinearity of 16 LSBs, you can only count on the DAC delivering a true accuracy of an 8-bit DAC because the low-order 4 bits, they're just not going to be reliable. First, let's talk about something simple, settling time. Now, simply put, that's just the amount of time that the DAC needs to settle to a new value after a sample is loaded. It includes the time the DAC requires to load and deliver the sample to the actual DAC circuitry, the time the DAC needs to slew to the new value, and the amount of time the output needs to settle following any overshoot or ringing on the output circuit. Overall, the lower the settling time, the better, and the higher the DAC output frequency can be. Next up is a specification with which you're probably familiar, and that's harmonic distortion. Harmonic distortion refers to the addition of unwanted harmonics of the input signal into the output signal. Most often, this is the result of nonlinearities in the signal chain, and that kind of makes sense. Think about a perfect sine wave in the frequency domain. It has just a single impulse at the fundamental frequency. Now, if you pass the sine wave through a nonlinear network, the output of the network is no longer sinusoidal. It's a distorted sinusoid. And a distorted sinusoid will invariably contain harmonics of the fundamental frequency in the frequency domain. The most common measurement of harmonic distortion is total harmonic distortion, or THD. THD is computed by taking the square root of the sum of the squares of all the distortion components, and then taking the ratio of that computed value to the full-scale signal. As we noted before, you can express this value as any kind of ratio, but most frequently you're going to see this expressed as a decibel measure. But harmonic distortion isn't the only source of dynamic distortion. Think about it. When we quantize each sample, we're adding significant distortion right there by forcing a natural, continuous signal to assume discrete values at precise time intervals. Now, in the time domain, Nyquist gives us a useful rule of thumb that we have to generate output samples twice as rapidly as the highest frequency we want to resolve. But we're not just sampling, we're also restricting the output signal to a set of predetermined levels in a process called quantization. And that process introduces a form of distortion known as quantization error. The noise component in the output signal is called quantization noise. Now, the good news is that just like Nyquist's law tells you how fast you have to sample to reproduce a particular frequency, there's also a rule that tells you how much quantization noise to expect. The signal to quantization noise ratio is always 1.76 dB plus the number of bits of resolution in the DAC times 6.02 dB. In a 12-bit DAC, the SNR due to quantization noise is 74 dB, and that means a 12-bit DAC will never have a better overall signal-to-noise ratio than 74 dB, since the quantization noise is baked into the sampling scheme. Now, both harmonic distortion and quantization noise tend to push the output away from the ideal values that we'd like to see. But there are still other factors at work. Electrical noise is another reality. The circuitry that builds the analog output of a DAC and the amplifiers that buffer the output signal are not perfect, and they inevitably introduce electrical noise. These noise factors add to the harmonic distortion and the quantization noise to further corrupt the desired signal. The ratio of the total power to all of these corrupting influences is called the signal to noise and distortion ratio, or SINAD. Now, SINAD turns out to be pretty important because it tells you a lot about the data converter in just one number. In particular, it keeps the designer honest. It's easy to convert SINAD to another measure called the effective number of bits, or ENOB. Now, remember when we computed quantization noise and observed that it was equal to 1.76 dB plus the number of bits of resolution times 6.02 dB? Well, it turns out that we can work that backward. Just subtract 1.76 from the SINAD and then divide by 6.02, and the result is the effective resolution, given in bits. Now, note that the ENOB will always be less than the actual number of bits of resolution, since one of the components of SINAD is the quantization noise. The bottom line is that when considering the accuracy of a DAC, you have to take into account all of the potential sources of distortion and noise. Now, before we leave the topic of dynamic specifications, we need to look at two more factors. The first is called the spurious free dynamic range. It works like this. As we saw before, it's not unusual to see spurs appear at harmonics of the reference signal. That's pretty much the definition of harmonic distortion. The ratio between the signal and the largest of the spurs is called the spurious free dynamic range, or SFDR. It's just one more consideration when you're thinking about how noise might impact your application. And then finally, let's talk about glitches. Glitches are undesired spikes in the output signal. Now, you might intuitively think that the amplitude of the glitch is the thing you have to worry about. But the amplitude is only part of the story. More significant is the area under the voltage waveform. Now, you're going to hear this called the glitch energy, but that's not technically correct. The unit measure for this area is volt seconds. And that's not the same as energy. Energy is measured in watt seconds. But nevertheless, the glitch impulse area is an important measure that lets the designer know what kind of noise to expect in the output. And those glitches can come from a lot of different sources. If the DAC is a clock design, you may see vestiges of the clock signal leaking through. If the DAC is a parallel load design, you may see a glitch when all the digital inputs change at once. The IC datasheet may have a value for the glitch impulse area, but keep this in mind. If you run analog traces near the DAC digital inputs, your PCB design can contribute noise. The lesson is clear. Getting the best performance from a system that includes a DAC involves choosing the right device with the best specifications for your application, and then designing the rest of your system to protect the integrity of the performance of the device. Okay, that's it. Now you understand how to read the specifications for a digital to analog converter and what trade-offs you might have to make with regard to speed, resolution, and noise factors.
For more information on this topic, please go to our website at www.maximintegrated.com under Products, Analog, Data Converters. We hope you enjoyed this video and see you again in another educational video of Maxim Integrated.